Hi, yeah, GM everyone. So yeah, I'm Josep. I basically work at ACI, an Aave delegate platform led by Mark Zeller. And I'm also CTO of Turing Consulting, which we basically do gas audits, security audits, technical due diligence for VCs and institutional stuff, which is kind of boring. So yeah, today we will talk about a little bit of what are the actual Ethereum proofs that we have, but it's kind of a technical talk, so I will try to build everything up from what is a Merkal tree, how it enables us to do these kinds of things that we actually like and we can use to save gas. And I will also, pues, obviously explain how to get the proofs and everything, but it will be starting slowly by the concepts, and then we will see how it goes. So let me check how this works. Oh, perfect. So most of you probably right now think that gas optimization is about changing a for loop from right to left, left to right, sorry, and it's just about, okay, I will just save the length before so I don't have to access the memory each time, and then if the context is correct, I will just do an unchecked to someone, to the iterator. But the actual idea of the people that work on gas auditing every day, most of the things that we do are on Yule and assembly and things like that. But we will see that it's not just about having some set of rules and just like that, but it's also about actually understanding how the thing works and doing architecture things when are needed, which is basically the way that you will save more gas. Here, maybe you will save 60 gas. By doing a huge architecture change, you will probably get a hell a lot of a discount, right? So let's start by a very simple thing. Just what's a Merkal tree? Okay, so a Merkal tree is a data structure. I'm sure that most of you are familiar with it. But just keep in mind, let's imagine that L1, L2, L3, and L4 is some data, whatever data. Then what we do is store the hashes of this data. And then we have, as we can see, hash of L1, hash of L2, hash of L3, hash of L4. Most of the time it's a binary tree, so it's completely symmetrical. We have like, for one parent, we have two childs, and like that. And then basically what we do is hash the two children that a parent has and basically set their value on there. So it's called Merkal tree because if you look it on reverse, it looks like a tree. So we call the top hash a root. Then in the middle, we have the nodes or branches. And then the data under it, we call the leaves, which is basically like a tree. So most of you, maybe if you are not familiar with this data structure, you are thinking that why is useful to hash things and save it in a strange manner instead of just having the data. But we will see that the Merkal tree has like a lot of characteristics that are very useful for especially things blockchain related. One of them, for example, is that let's imagine, okay, that I have the L1 data, and I want to prove that the L1 data is inside of a tree, right? So I could get the top hash, save it on the blockchain, just the top hash, and then by using the L1 value and the hashes that I need to go into there. So for example, I will just move here to make it easy. This is kind of like a class, not a talk. So if I have this data and I want to prove that it's here, I will need to know this hash and this hash. So I will be able to create this hash from my leaf. Then I will be able, obviously having this hash, to get this hash. And then with that hash, I will be able to get the top hash. So this is kind of what we call the proof. We will see an example after this. But basically, we can verify that we have some data inside of that tree without just having to store the actual root. And this is something very useful on blockchain for something that most of you probably will hate, which is NFT whitelist, for example. Most of the people, at least maybe some years ago, they thought that, by the way, uint is a typo. It should be an address or something like that. But most of the people think that, okay, let's imagine I want to get rich fast, PFP collection, you know. I need a whitelist to know how many people can mint or whatever, or the amount or the price or something like that, because as I obviously want to scam people and get more money, maybe I want a discount, but the code needs to be the same on the smart contract. So I will just put me and my friends list on a whitelist. And yeah, most of the people think about like an array or a mapping or something like that, but that is something that is very expensive for the deployer if we are talking about 10K addresses, right? Because you need to seed the data. You need to, for example, I don't know, if you batch transactions, maybe you have to do less transactions, but maybe you will have to pay for 5,000 transactions on Ethereum in order to put 10,000 addresses on a whitelist array. And the same thing happens with a mapping. Here, though, like we have a difference, and the difference is that if we actually have a mapping with the entire data, it will be quite good for the user to just get the information from this mapping and being if he's on the waitlist or not. But instead, if we have like an array, it can also happen that, let's imagine that we have like 10,000 people on a whitelist or something like that. If you are maybe the person that's on the last position of the array, and they somehow iterate over the array in order to get if you are on the whitelist or not, maybe you will never be able to mint just because probably the gas of just iterating 10,000 times a loop on Ethereum will be more expensive than what a block can handle, or at least your transaction or your wallet or whatever. So this is something that we literally discard. We don't want this. And this is like an example of what we saw using a Merkal tree, right? So let's, as always, Alice, Bob, we look like we are cryptographers, but we just use two names. And then, for example, I want to save like the address of someone and the amount of NFTs that they can mint at some point. So one of the ways that we can do that is obviously with a mapping with a struct or something like that. But the point of this thing is to understand the Merkal trees in order to get into the proof that we have actually on Ethereum. So yeah, for example, I'm Alice, I know my address, and I know that I should be able to mint 5 NFTs. So I will get this data, I will hash it, and then with the what we call the proof, which is like the hashes of the nodes that I will need to get in order to hash again the data, in order to get the root. I know it's complicated, like I will do again like this on the graph. But basically and I come here again, like if I'm Alice and I know my address and the quantity of NFTs that I have to mint, I basically get a hash here, which is this one. So in order to verify that I'm inside of this Merkal tree, I will have to have this hash and this hash. And why? Because as Alice, I will get my hash. If I hash it with the first element of the proof, which will be this one, I will get this hash. And if I hash it again with the second element of the proof, I will get this hash. So this, theoretically, and I hope it helps you understand what a Merkal tree is and how it works. And especially with this dynamic that I explained right now, you should notice that if I want to store 1,000 addresses on chain or 10,000 or whatever for doing whatever thing, I just have to store the root inside of the blockchain. That means that instead of storing whatever data, you have to store most of the times like 32 bytes of data. And also like this kind of verifying or proving that something is inside of the Merkal tree is expensive gas-wise, because you need to, as we saw, like recalculate the entire tree in order to see if the root that you get is the same one as you have stored in a smart contract, right? Okay, so sorry, this is great, but this is not what an actual Ethereum proof looks like. And there's a concept right now that most of people don't really know, which is called RLP. RLP is kind of a serialization thing between nodes of Ethereum and clients, and no one understands what it is, actually. No. It's very easy, but it's just, I don't know, some specification that they have in order to communicate between each other. And this is like very weird at the start, but basically we have an RLP, which is this kind of serialization instead of this hashing of some values, right? So I just want to introduce a little bit. As I said, like this is like, I will teach some concepts in order to understand the entire picture. So what is like a serialization, and especially RLP? So it's basically a very simple set of rules. So for example, the first rule is when you are encoding a value which is only one byte, and the decimal falls into 0 or 127, then the RLP representation is basically the hex value of this decimal value, right? So for the number 120 to RLP, we get 78, which is basically decimal to hexadecimal, right? And we basically have like a lot of rules like this. I will just mention the second one and then we'll be over because it's not like the point of the presentation to understand exactly how this serialization works, but just to have like a better picture of everything. But for example, and this is kind of curious, when you want to encode a string, well, serialize, not encode, and the length of this string is less than 55 bytes, you basically have like a very simple calculation, which is like 0x80, well, you have it there, 0x80 plus the length of the string and then the string itself. So it's like very small there, but the string doc, which is obviously DOG, it has a size of 3, which is like the length of the actual string. And then we have the hex values of the letter themselves. So the string doc encoded would be just like 0x83, which is like 080 plus 3, and then DOG in hex value. Okay, so as I said, like it's not the purpose of this talk to just understand what RLP is and how it works, but I hope that you will get like a better understanding of how it works and why is that. And here becomes like the key of the actual presentation. This was just like some kind of giving some context. Because these trees that we use on Ethereum are actually serialized with RLP. So just talking about the use case here, and we have great guys there from VGD that they deployed governance v3 of Bové, and they are on voting phases right now and things like that. No, but well, one of the problems that we have right now, especially in governance tokens, is that you must know what voting power you had at a specific date, right? So let's imagine the Aave DAO, for example. If you want to vote on a proposal, I need to know how many voting power you had on that proposal block, right? So if I transfer tokens and I do things like that, I will see that I have to do some extra operations in order to do snapshots, to save the data in chain, to basically specifically get this. So this means that for the end user of the token, not in 20 days, but as of now, they need to pay a little extra gas in order to have this extra tracking that we need these capabilities, right, for the actual governance. But the good thing, and this I want you to think it like as kind of the events that you know, especially on the blockchain, which is like something that we create on the blockchain, but that we cannot actually read inside of the blockchain. Like, I know this is like a hard concept, right? Why are events stored kind of in the blockchain, but I cannot read them, but I generate them from the blockchain? So we have the same thing with proofs. We cannot access these proofs from the blockchain itself, so we need to have some kind of program or API or robot or whatever that gets the proof for us, and then we can verify it on chain. But we have like transaction tries, state tries, receipts tries, which is basically a lot of Ethereum data. It's not something that we will enter on. We will just focus on the state root and the storage root, which is just one Merkal tree, similar to the ones that we saw before, that will enable us to prove that at some block, on some address, which could be an smart contract, at a certain slot, we had some value. And that means that we could completely delete this overhead on all the transactions of all governance tokens just by using this. So as I said, like these proofs are kind of like events, right? Obviously not events, but you cannot access them on chain, so you need to generate them off chain for now. And basically you have like this get proof method on most of RPCs. Like not all clients support it, but if you use Alchemy and things like that, you have it there 100%. But basically, sorry, when you call get proof, you need to send an address, a block number, and you need to also send the slot. So I'm pretty sure that you are familiar that the storage in Ethereum works by slots, which is like 32-byte like space and things like that. But in this example, I just got an entire random address, which is the one that we see on the top. And I ask for the slot 0, so the first position of the actual storage of the smart contract. And we can see that I get like an address, account proof, which is not something that we will use right now, but as we saw on the Merkal trees, we already have some kind of proof to do calculations of this account, especially to check the code, the nonce, or the balance. So we could actually use this to check it. And then we have like the storage hash and the storage proof, which is the thing that is interesting for us. The storage hash, well, is basically the root that we saw. And then we have the key, which is the slot, the value, which is, in this case, no, it could be the voting power. And then we have the proof, which, as we saw, it's like the path to be able to reconstruct this Merkal tree in order to verify it. So this is code from Aragon. I would prefer to use Aave v3, but it was not already live. So basically, we have like 3 easy functions here, and I don't want you to go like fully technical into this, just because like there are changes obviously on Ethereum versions and things like that. I want to just give you like the general overview to try to understand how everything works and how can this be useful. But basically, the first thing that we need to do, as we said, like this is some data that we will be putting from off-chain. So the first thing that we need to do is to get this actual root from a block header and verify that this header is correct. So just keeping in mind that if you are able to put on a function to verify your own root, your own leaf, and your own path, you can basically make everything valid, because you can create your own Merkal tree for whatever, and it will be always OK. So we need to set some constraints, and this, most of the times, the constraint is basically getting the correct root on chain in order to then be able to verify all these things, right? So I have like a length check here, which is just for, because I use then an mload to load some things in memory. But yeah, basically what we do is get the state root from the block header and verify that this block header corresponds to a block hash. So it's not a lot of things, it's actually just some kind of simple verification that we'll need to do. Then we have here some kind of cache. And basically, as we said, like this kind of reconstructing an entire Merkal tree to verify something is not very cheap, because we need to, well, it is cheap, as always, no, if you have just 2 elements on the proof, because you need to reconstruct the Merkal tree and just do 2 things. But if you have a Merkal tree, which may be 9 proofs, it means that you need to get the proof hash, proof hash, proof hash 9 times, and then in order to get if the root is correct or not. Which also it could lead, no, theoretically into like a DDoS attack, or not DDoS, but at some point, if you have like a huge Merkal tree with a lot of proofs, maybe you won't be able to verify it on chain because you won't be able to pay for the gas or the block space or something like that. But yeah, well, anyways, what I do here basically is to get the storage root of a certain block number for a certain account of this blog, like of the thing that we saw before, like the request that we did at Ethereum Get Proofs. And I basically save it on a mapping, which is called storage root, just because, and I'm sure that that happened at some point when they were deciding how to do governance v3 at Aave. They want the users to be the one that have like the cheap experience. So they will cache everything in order for the user to then just, when they want to vote, they just come, read the mapping, that's cheap, and everybody's happy, because we have more voting participation, and then the user can vote for a cheaper experience, right? So here, basically, what I do is just save the storage root for account on a certain block number, and then we have like this beautiful function, which is like a get storage function that we can create by using the 2 functions that we saw beforehand. We can basically send the account, the block number, the slot, and the storage proof. And we will see exactly the value that we had on that slot on that day. It's like a storage oracle, but using these off-chain Merkal trees. And yeah, basically, this is something that I don't know if VGD has done the calculations, but right now on the Aave token, we have like on a V4 transfer, we have some hooks in order to get this delegation thing going and everything. And maybe just, this is just something like an imaginary number, right? But imagine that you save 1% gas on each transfer from now on. That could be like a lot of money for the Aave DAO, the Aave users. and basically for all the governance tokens out there that need some kind of snapshot tracking. I also want to say that this is the storage route, but you can also prove Ethereum balance at some block and things like that. So there are a lot of possibilities. I hope that I gave you a little bit of the big image of everything and try to build up into understanding exactly how it works. But yeah, that's it. I hope you like it and have a good day here at SmartCon.